Good morning. Welcome to Krishna's class. Today we explore the Parseval's identity. In fact, we have the Bessel's inequality that we have already proved. And when equality holds in that case, this is the question that we are asking. When equality holds in that case for all x, how to characterize the situation where an equality holds in the Parseval's equality. Now it turns out that the restriction is on the basis that we choose, and the basis, on the orthonormal set that we choose, and if the orthonormal set has the property that it is a maximal orthonormal set, which I shall explain soon, or what you call an orthonormal basis, or then it follows that equality holds in the Bessel's inequality. And this means the following, that such an equality is often called Parseval's identity. Okay, so we will come to that. Before that, we look at something called the polarization identity, which in fact connects the inner product with the norm. Now just recall the following. Before we prove the theorem that I have put here, the theorem is, of course, our basic assumptions are H is Hilbert space over the field C. Now, theorem that we prove is, in an inner product space, the inner product is expressed in terms of the norm. For every x and y, the inner product of xy is equal to 1 by 4 norm of x plus y whole square minus norm of x minus y whole square plus I times norm of x plus iy whole square minus I times norm of x minus iy square. Now this particular relation is what you call the polarization identity. Okay, let us recall something that we have already. If you recollect, then we had two terms. One is, of course, inner product space. The other one is what is called a pre-Hilbert space. Now, what is an inner product space? It's a vector space with an vector space with an inner product. And what's a pre-Hilbert space? A pre-Hilbert space is a normed linear space it's a normed linear space with parallelogram. Of course, if you have an inner product space, is a normed linear space, and the norm satisfies parallelogram. That is something about the inner product space. Now, a pre-Hilbert space is something. So, a pre-Hilbert space see, this is a characterization of a pre-Hilbert space or an inner product space. So, which normed linear space is an inner product space? So, I will put it that way. So, we ask the question, which normed linear space is an inner product space? So, a necessary and sufficient condition for a normed linear space to be an inner product space is a necessary and sufficient condition for a normed linear space to be an inner product space. Is that the parallelogram law? What does it say? It says norm of equal to this is parallelogram. See, the point is this. So, if this vector is x, this vector is y, then you know that vector additions take place through parallelogram law. So, complete the parallelogram. So, this is x plus y. This is the vector x plus y. And you see that A, C. So, in OABC, so OACB, we have norm of length of OC square plus length of AB square. That is square of the sum of the square of the diagonals is equal to twice length of OA square, length of OB square. This is the parallelogram law. This is the basic property of a parallelogram in R2 or R3. which we are familiar with from the classical geometry. This is clear. And this classical geometric structure is there in a normed linear space where the length of a vector is designated by the norm. Then you see that this is essentially, you compare this with this, you see that OC square is x plus y whole square, AB square is x minus y, norm of x minus y whole square, and that's equal to twice norm x square plus norm y square. Okay, this is the same. So this is what is called the parallelogram. Okay? Taking looking at the similarity of the problem. Now, what we have said is that this is a necessary and sufficient condition in a normed linear space for the norm to be derived from an inner product. Okay, this is a beautiful theorem, and proof is given by, this is actually Frechet, then Jordan and von Neumann. I have not proved this. I think I have proved this theorem earlier in my lectures on inner product spaces. Possibly, I don't remember now. But otherwise, the proof is available. Refer to K. Yoshida, functional analysis. You see, the reputation of the people who have proved shows that it's an extremely important result. And one way the theorem proves very easily, namely that if you have an inner product space, then the derived norm satisfies the parallelogram norm. That is very easy to verify. The converse is difficult. Okay. Why it is difficult? Because all that we know is you are given a normed linear space satisfying a certain condition, namely the parallelogram law. Okay, right? So you have a normed linear space where the norm satisfies the parallelogram. So the question that you ask is this norm derived from an inner product? The answer to this is yes. Therefore, you have a nice characterization theorem, and you can see that these very important mathematicians of high repute who have put their, it's a beautiful result. It's a very nice structural result on inner product spaces. Now, in this context, you see that how do you proceed? So we have to first cook up a possible inner product. Okay, a possible inner product you have to cook up to verify that it is indeed an inner product. Okay, so how do you do that? So you take this relation. Suppose you are in an inner product space. Then what is this? This is equal to x plus y, inner product of x plus y with inner product x plus y. This is inner product of x minus y with itself. This is inner product of x plus iy with itself. This is inner product of x minus iy with itself. Then you apply the normal rules of expansion of this, and you will end up with 4 times inner product of xy. Therefore, from that we define inner product of xy to be, possibly if at all it is so, this is going to be the case. So the inner product will be defined as the corresponding complex number, namely 1 by 4 norm of x plus y whole square minus norm of x minus y whole square plus I times norm of x plus iy whole square minus I times norm of x minus y whole square. Okay. This is the one that we take as the definition. And then you indeed prove that this particular, because this is essentially a map from the normally linear space. Suppose you call that normally linear space X, then it is a map from X cross X to C. This gives an X. This defines a map from X cross X to C. So it's a complex number that comes out because you see we notice the I sitting over here. So it's a complex number. Okay. So it puts every xy, ordered pair xy in X with a number. Okay, it's not very easy to see that it's just all the properties of the inner product. And what are the properties of the inner product? It's linear in the first variable, conjugate linear in the second variable, x is equal to norm of x square. That is possibly very easy to find. And then inner product of x with itself is greater than or equal to 0 and equal to 0 if and only if x equal to 0. Then what are other properties? Cxy conjugate is equal to the inner product of y with x, or the inner product of y with x is actually the inner product of x with y conjugate. That is something. Those are probably easy to verify, very easy to verify. But the difficult part is to verify that this is linear in the first variable and conjugate linear in the second. Conjugate linear in the second variable would easily follow, but this one is somewhat difficult to prove. And you can see that the proof of this theorem essentially dwells on this particular space. It's a beautiful result. Okay. So I am not going into the proof of that. I accept that if you have an inner product space, then the inner product and the norm are connected through what is called the polarization identity. Okay. Now I just suggest that you do the following proof outline. So I just put the outline of the proof. Okay. We outline the proof of this theorem. Outline. Use the facts and then go for its expansion. Okay. And this would turn out to be and also you need to give what this means. which you can write as plus, and on the side, I'll write it this way. Plus IY, forgot the date, which you can write as and then use the following facts that equal to so use these properties, and then of course you have these properties you use and then expand it. If you expand it and simplify this side by substituting these things in the inner product form, and then a lot of cancellations take place, and eventually you are left with 4 times inner product of x. So I leave the proof. Okay. Okay. So that's a nice relation connecting the norm and the inner product. Okay. So you have seen that if you have a pre-Hilbert space, that means a normed linear space where parallelogram law holds, and set or denote by xy, inner product of xy as this relation, or this relation as this relation. So if I this star, the right hand side of star is essentially the inner product from which the norm is derived. This is the theorem that you have. It's a beautiful theorem. Right. So let me now come back to the central theme of today's lecture, namely, let us recall the following. So you have an x hat and h, the U alpha. A is an index set and orthonormal set. Obviously, it is a linearly independent set. And further, you can, A is an index set. Not necessarily. Finite or countable. Could be even uncountable. It would be nice to look for an example of a Hilbert space which has an uncountable pieces. Right. Then you have the L2A. Consists of psi alpha with the property that is finite. You know that this is an inner product space, and it's even a Hilbert space because it is complete. You can show that it's complete, and the square root of this essentially gives the square root of this gives you the inner the norm of the vector L. Okay, so psi half, and of course psi eta inner product is actually summation over alpha become A conjugate. Okay, this is what you have in L2E. Now, what we have proved earlier is that with no assumption that this is some orthonormal subset in H. We have proved that there is a continuous map from the Hilbert space to L2A. Okay, and if you take a subspace of H, which is the linear, which is the what do you call the closure of the span of the orthonormal set, then the map that I have mentioned earlier from H to L2A restricted to such a subspace is indeed a onto a map, and it's also an isomer. And now this is what we have to do this time. So just recall the theorem that we have ever used. Now let me make some definition. And after that, we will state the main theorem. U alpha belonging to index set A is a maximal orthonormal H if any X inner product of X with U alpha equal to 0, alpha belonging implies or in other words, it's only the zero vector. It's only the zero vector that is orthogonal. That is, if only zero vector has the property is orthogonal is called maximal Okay. Maximal, or we also remark the other names for maximal orthonormal set. Maximal orthonormal set are called complete orthonormal sets. That is another terminology for that. Orthonormal set, that is one name for that. Or an orthonormal basis in fact you can describe every vector in H as the limit of a sequence of vectors obtained as a finite linear combination of vectors in U alpha. Okay. So this is the meaning of saying that it's an orthonormal basis. Or you say that, or in short you say that U alpha spans H. Spans H in the sense that if you take any linear combination of vectors in this, whenever you talk about linear combination, it means only a finite sum. Okay. The whole collection would form a subcollection of H. But the property of this subcollection is that it is dense in the Hilbert space. Okay. Or in other words, you can reach from this orthonormal collection, the whole space by taking finite linear combinations and through a limiting process. That is the meaning of it. Okay. Now let us state the theorem. This is the main theorem that we are going to today. Be an orthonormal set H. Then each of the following statements are equivalent to the other. So I am giving 4 statements below, and every statement implies the other 3. Okay. So that is the meaning of this. Okay. So what are the statements? Let us write down. The first statement is that a maximal orthonormal set or what you call an orthonormal basis for the space. Okay. Or a complete orthonormal set. These are all the various terms. Second statement is that the set P of all finite linear combinations the collection U alpha is dense You can talk about density and all because you have already an inner product and therefore a norm and therefore a distance. So it's a metric space. The equality so we call this 1. The equality complex conjugate inner product of x. Now the first one, the equality 1 and equality 2, you see that equality 2 easily implies equality 1. Incidentally, what is x hat alpha is the what are called the Fourier coefficients of f. I'll just write that. Of x belonging to okay, and the first equality is in general an inequality. So that we have already proved, and that is called the Bessel's inequality. Okay, there we are not assuming that U alpha is a maximal orthonormal set, but if not only that U alpha is a orthonormal set, but is also a maximal orthonormal set, in that case, equality holds in the Bessel's inequality for every x. And the equivalent form for inner product is given by the next statement. So 1 implies 2, 2 implies 1. Okay, but let us prove this theorem. This is a nice result. So we'll make some remark before that and give the names. Is called the Parseval's identity. And once we prove this, the equivalence of 3 and 4, 3 is also called the relation 1 is also called equilevel equilevel 1 is also the Parseval's identity. That is because of the equivalence of the two. Okay, so we will just write this. Now we give them. I can give proof. Showing that by one so this cyclic relation. There is 1 implies 2, 2 implies 3, 3 implies 4, 4 implies 1, and in that, if you use this cyclic results, okay, you can essentially get any one of these 4 statements is equivalent to any other, the other 3 statements. That's the usual standard. Okay, let us prove this. So the first task is, okay, let us just recall what we have, what are our assumptions, or recall what we mean by U alpha is maximal. U alpha is maximal means there is any x which is orthogonal to U alpha. Maximal orthonormal set the product x with U alpha implies equal to 0. So this is the statement. That is, there are 2 statements here. This is maximal and this is the second statement. Okay, so we'll be using it in this particular form. Okay. So how do we prove this? So we prove by showing that not 2 implies not 1. That means if 2 is not valid, then 1 cannot be valid. So that by the counterpositive argument, if 1 is satisfied, then 2 is a consequence of that. I mean, that's very easy to understand. Okay, that is the standard procedure, and this is true. Okay, not 2 implies not. So this is the strategy that we. Okay, so assume it's not. What does this mean? This implies P closure is not equal. Okay, which implies there exists x belonging to H x not equal to 0 such that x is orthogonal to p. Okay. What does this mean? That is, this is also stated by saying that x belongs to p per. Thus, we have an x which is not in P and therefore not among U alpha, okay, which is not equal to 0, such that it is orthogonal to every one of these U alpha, okay. And since x is not equal to 0, you can normalize it, okay. So you can use this U defined by norm x. Is not equal to 0 and norm U equal to 1. Okay, right? Further, contradicting the maximality of U alpha. Okay. Thus, maximally H implies equation equal equation equal to H. That is, the set of all finite linear combinations of U alpha is dense in H. Okay. So that completes the proof of 1 implies 2. Now we take 2 implies 3. Once again, we use the same technique. Okay, right? So, this implies where x is some x belonging to H, for which what is the property? Is strictly less than norm of square. Okay. Now consider y equal to x minus alpha belonging to P. Okay. Then what do you have? Now observe the following. Norm of y square. This is the inner product of y with y, which turns out to be inner product of x with x conjugate x u alpha minus we are using orthonormality here and get conjugate. Okay. Now what is this? You see that x equal to alpha. So use this. Therefore, norm of y square substitute that and you get the complex conjugate. Therefore, you should get essentially is not equal to 0. So y is not equal to 0. And y belongs to P closure. Okay, y belongs to P closure, right? This you can verify easily. Y u alpha to this is equal to 1. Therefore, you have and this is 0, and for y x alpha, that's what we want to. Alpha belonging to, so y is orthogonal to per of this connection. Okay, and y not equal to 0. Thus, enclosure not equal to 0. Okay. Consequently, what we have is h, then see that form of so the Parseval equality holds here. Okay. Now we prove the next one is now we prove three implies 4. So assume then what we claim is this. For every x, y belonging to, this is the claim that assume this. Okay, so here we use polarization. from which you get so we observe the following. X is equal to so x plus y therefore norm of whole square. This is by whole square. So these are the four relations that you have. Now add and then divide by 2. Therefore you get equal to, see, this is simply this. You simplify this. You simplify this. This is what we have done. I am just skipping the calculation. These are all complex numbers. So you are just adding them. It's very easy to work down. I times so just complex numbers. You know that now use okay. This way, this what is the final outcome? This is equal to 4 times conjugate. So this you verify. A into A conjugate and expand, then this is what you end up with. Okay. Thus, okay. So this so you can check where exactly we have used this. Somewhere here we have used the property 3. Okay. So now all that remains is the following. It implies one. Assume one is box. Not equal to 0. Because we are assuming this is not maximum. Okay. That's the reason. So there exists a u not equal to 0. Okay. What is the consequence of that? Then not equal to 0. conjugate is equal to this is equal to 6. What does this mean? We have taken u equal to x. And is strictly greater than u, which is equal to sigma conjugate, which is equal to 0, because you take this is equal to 0, right? Okay, what does this mean? Equal to. So if 1 is false, 4 is not true. So not 1 implies that is if and only if so that completes the proof. So we have completed the cycle. 1 implies 2, 2 implies 3, 3 implies 4, and 4 implies 5. Okay. So we have completed the cycle now. 1 implies 2, 2 implies 3, 3 implies 4, and 4 implies 1. Okay. So that completes the proof theorem. Okay. So I think we shall stop there today. Maybe I'll be coming back for the next lecture, maybe after a week, because I'm leaving for Bangalore for 1 week's time. Okay. Thank you. So we look forward to have a nice time. Look forward to all of you having a nice time. Thank you.